Hello, welcome to another chapter of the same story. So we're still examining electrostatics, okay? We're still talking about point charges and electric fields, forces, okay? But now we're examining that in the context of energy. So these are the sections in chapter 17 that we're going to cover. I think we're going to get through everything. We might leave off dielectrics. But other than that, we're gonna do most of the chapter here. These are the learning goals for the chapter. Revisit those when you are studying and make sure that you can achieve all those learning goals. And this is going to be really important. I do have a review slide here to cover some of these concepts. So to be successful with this chapter, you're going to need to recall some definitions from chapter 6. Work done, okay? The relationship between a conservative force and the potential energy, and I'll go over that in the next slide coming up, next couple slides. As far as the generalized expression for gravitational potential energy, you don't really need to remember that, but there is an analogy between gravitational potential energy and electrical potential energy. So that may help you with some conceptual understanding. And then finally, we need to recall what the electric field due to a point charge is. All right, don't worry about sheet of charge. We're not going to examine that situation. We're going to stick with point charges. So, what is electric potential energy? Well, we have an idea of what potential energy is. Electric potential energy changes when a charge moves in an electric field. All right, so let's go over some of those concepts from chapter 6. And I will rewrite those notes there. So recall the definition of work. Okay, work done on an object by a constant force is given by multiplying force, magnitude of the force, times the displacement of the object. Okay, and so if they're in the same direction, like in this particular equation, then the result is positive. But if they're in different directions, so if the force vector is this way, and then we're moving an object opposite to the force vector, let's call that D vector, then your work, this is a situation where work is negative. Okay, so recall that's how you define work in terms of a force and a distance. And so, well, what force are we going to be talking about here in this chapter, chapter 17? We're going to be talking about F equals QE, right? The force that a particle feels in an electric field, or the force that a particle feels when it's near another particle. So we would substitute QE into F, and we'll be doing that. So there's another way we can define work done. If we have knowledge of the velocity that the object is moving, we can define work done by its change in kinetic energy, okay? Where Kf minus Ki is simply delta K, right? So anytime we have a delta, we have a triangle there, that means final minus initial. So we can also define the work as change in kinetic energy, where kinetic energy is 1/2 mv squared, which I'm sure you remember that from physics 1. It's one of those equations that always is probably going to be burned in your mind for the rest of your life. So the work done by the net force on an object, okay? So if you add up all the forces and you get a resulting force here, the work done will also be equal to the change in kinetic energy of that object. And so finally, what if this force is a conservative force? Okay, guess what? Electric force is a conservative force, just like gravitational force. And if that's true, which it is, then any change in kinetic energy is going to be equal to negative change in potential energy. If we make this substitution here, we see that work done is also equal to negative delta U. Okay, where delta U is the change in potential energy, right? Negative delta U is negative U final minus U initial. And where does that come from? Well, remember the conservation of energy. All the energy changes in the system are going to equal to zero. That's the conservation of energy. And this delta K equals minus delta U is just coming from solving that equation right here. Okay, and so what are we looking at here? What are these all just random equations put together? No, there are three different ways we can express the work done. And so we can equate all these together, right? If we can express the work done as FD cosine theta, and well, we can set that equal to delta K, or we could set that equal to negative delta U. So it gives you some problem solving options. Okay, so that's our review from chapter 6, these definitions. And now, instead of applying them to a situation in chapter 6, which was pushing a box, letting gravity pull a box down a ramp, blah, 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 now we're talking about charges in electric fields and the forces that they feel, such as the attractive force when the particles are oppositely charged, or a repulsive force when the particles have the same sign charge. So, but let's go back. I think this is going to be helpful just to get us used to this terminology again, just kind of a refresher. So what's really great about electrical potential energy is that it's analogous to gravitational potential energy, and that's because both of these forces, the force of gravity and the force of electrical attraction and repulsion, these are both conservative forces. And so being both conservative forces, they're going to behave the same way, and their potential energy is going to change in a similar fashion. So let's take a look at that. Let's recall, right, if we have a ball and we're standing on the surface of the earth and we're lifting this ball up, okay, its height is increasing. Well, what's happening? Its gravitational potential energy is increasing. So let's kind of dig into that. Why is gravitational potential energy increasing? Well, let's look at the forces. What is the force that this ball is experiencing? It's experiencing a force due to gravity, which always points down, right? Gravity is always pushing us down to the ground. So that is the direction of the force, but our displacement is up, right? Because we're moving the ball up. So the displacement vector is up. And if we use our definition of work, which is force times displacement times cosine of the angle between the force vector and the displacement vector, then we're going to get FD cosine of 180, okay, which is giving you a work that's less than 0, right? Because this guy is -1. So I realized, okay, I just threw cosine and theta on there. If you go back to chapter 6, you'll see that this comes out to be FD cosine theta. This particular equation is just showing you when it's only the same direction, but for any arbitrary direction, it's FD cosine theta. So we have a work less than 0. So how does that relate to the potential energy? So if work is less than 0 and work is equal to negative delta U, well, then the two negatives are going to cancel, and you're going to have a delta U greater than 0, right? So it's implied here that this is a negative number. So we have like a kind of an imaginary negative sign in front of it. Those are going to cancel, and you're going to be left with a delta U that is positive. Okay, so we're going to be encountering in this chapter a lot of quantities that are represented as variables, but those numbers can inherently be negative, okay? Just like this. So W is negative, but W is also equal to negative delta U. So that implies that delta U is positive, which is this little statement right here, okay? So, excuse me. So that's how we're interpreting why the gravitational potential energy is increasing. So this is how we interpret potential energy changes in the context of gravity. Now let's examine the change of potential energy in the context of charges in electric fields. So let's say we have a negatively charged particle and it's in the vicinity of a positively charged particle. If we are moving this positively charged particle away from the negative charge, we are also getting an increase in potential energy. And so this is going to be analyzed in the same way. What is the direction of the force that the positive particle is feeling? Okay, this is our D vector moving up. Well, it's feeling an attractive force, right? Because opposites attract. So again, we have our force direction opposite to the displacement direction. And so our work done is negative. And we also know that our work done is equal to negative delta U. So that implied negative in W cancels with the negative here. And we see that our change in potential energy is positive. Okay? So that is an analogy between gravitational potential energy and electrical potential energy. So the difference, though, between these two situations is that gravity, when we're looking at gravity, we don't have any situations where we have a negative mass. So we will never see a force vector pointing up for gravity, right? We'll never see that. We'll never see another massive object repulsed from another. So, however, in electric fields, you do have that opposite situation. So if I have I'll use yellow, if I have a negative charge, no, I'll use the same color here. Okay, if I have another negative charge here, same as on this side, but now the other charge is negative as well, and I'm moving it away from the negative charge. Okay, there's my displacement vector. What is the direction of the force in this case? Well, you have two negative charges, so the force direction that this negative charge feels is going to be up as well. And so now you're going to have the work done being greater than 0 because of the definition of work being FD cosine theta. And you also know that the work done is equal to negative delta U. And so since the work done is inherently positive, your change in potential energy is going to decrease. It's going to decrease, right? Because delta U is final minus initial. Okay, if I distribute this negative, it's initial minus final. Okay, and if that is equal to a positive number, that means this guy is bigger than the final position, right? So you have an increase in potential energy. A decrease in potential energy, right? You're going from big to small. That means you're decreasing. So understanding that is going to help you a lot with understanding changes in potential energy and keeping your signs straight. So let's bring up that definition again of work done, right? So the work done by a force to move a particle some distance d at any angle with respect to that force vector is FD cosine theta. But in the case of charges and electric fields, the force is QE. So we substitute QE and we can see that the work done by an electric force is QED cosine theta. Okay, where theta is the angle between E and D. And to find that angle, we place those vectors tail to tail. So now if we relate that to the work done, which is negative delta U, we can see that the work done is going to be equal to negative change of potential energy, or we can express it as a positive value delta U equals a negative work done. And therefore, the change in potential energy in this situation is going to be equal to negative QED cosine theta, which is right here. Okay, and so let's talk about this equation here. So this is representing the change in potential energy with respect to a particle moving in an electric field. And in this equation, there's some variables that are inherently negative and some that must remain positive. So the variables that can change sign, Q can be positive or negative. However, E and D must be, are magnitudes, so must stay positive. And finally, cosine theta can result in a positive or negative value, okay? So there's two variables here that can change the sign of delta U, and that's the charge or cosine of the angle between E and D. E and D are positive numbers. Okay, so that's going to help you a lot when we do these problems, is to know which variables can be inherently negative and which cannot. So that's going to help you keep all your negatives in the right place. So if the work done is equal to QED and the change in electric potential energy is negative work done, all right, let's look at some situations. So what if, let's look at this circled area here. So what if we have our particle moving with a displacement that is up? Okay, well, then our theta is 180 degrees, right? And our Q is positive here. So this is a positive value. And the negative stays in front because that's from the definition of work equals negative delta U, right? So we have the negative staying in front. Q is positive. E and D are both positive. Cosine theta is negative, okay? And so then these two negatives cancel. And what you see is that the change in potential energy is positive. If a positive particle is moving against the electric field. So now what if a positive particle is moving with the electric field? Well, then the displacement is down. Okay, that's the blue vector. And therefore, the angle between them is 0. We have our negative sign, which is part of the definition. Q happens to be positive. E and D always positive. And our +1 we get from cosine of 0, which is 1. And so what we see is that we have a negative change in potential energy, or that the potential energy is decreasing. Let's look at the case when the particle is negatively charged, okay? So if this particle is moving opposite to the electric field, the angle between the electric field and the displacement vector is 180 degrees. And the negative sign that is part of the definition is going to cancel out the negative sign from cosine of 180. And that's going to leave us with plus QED. But this value is going to be less than 0 because charge is inherently negative. Okay, so that negative sign is built into Q right now. That's why this statement is the way it is, okay? And so if delta U is less than 0 and work is equal to negative delta U, then the work done is going to be positive, right? Because this is negative, all right? And then that's going to cancel with the minus sign in the definition. So we get a positive work done in this case, okay? So now, if this negatively charged particle is moving with the electric field, so our displacement vector is in the same direction as E, cosine of 0 is 1. We have our negative sign, which is part of the definition, and embedded in Q is another negative sign. So those two negatives will cancel, and what we get is a change in potential energy that is greater than 0. And if that's true, if work equals negative delta U, then, and this term is positive, then the work done is going to be negative because of that inherent, or that negative sign that comes with the definition. Okay, so it's a little bit tricky because we're talking about Q, and Q can be inherently positive or negative. We're not pulling out that negative sign and placing it in front of the equation, okay? We're inherently speaking about Q being negative. which is why this term is negative. So let's do this example together. And we're going to practice, with our negatives, keeping them straight, keeping them in check, all right? So if we have an electron, which of course has a negative charge, and it has a mass, it's released from rest in a uniform electric field. The field points in the positive x direction. It has a magnitude of 2 times 10 to the 2. We want to find the speed of the electron after it has moved 0.3 meters. All right, so let's draw a picture of this situation. So we have an electric field pointing to the right. And we have a negatively charged particle. He's in that electric field. He's being released from rest, and so he's going to start off with 0 velocity, and he's going to start to accelerate. Why does he start to accelerate? Because he's feeling a force, right? When particles in electric fields feel forces. And so what direction is this force? Well, negatively charged particles, we know that F is QE. And so if Q is negative, that's going to flip the direction of E and make F in the opposite direction of E. So our force is going to be going this way. And so that means our particle is going to be moving to the left. Okay, so that means its displacement vector is also going to be this way. So let's use our definitions of work and how it relates to kinetic energy to find the velocity of the particle after it's moved. Okay, so we know from one definition of work that work is FD cosine theta. If we plug in QE for F, that makes it QED cosine theta. Okay, that's the definition of work. There's no negative signs in this definition. The negative sign comes from this guy or this guy. Okay, but we're not going to replace Q with a negative number until we're ready to put the math in. So for now, when we evaluate cosine theta, if we get a negative from that, then that's fine. So let's evaluate it algebraically. So the work done is the value of Q, magnitude D, and then the angle between E and D. So E is pointing this way, D is pointing that way. So they're going to have a 180-degree difference between them. So that's cosine 180, and there's a negative coming out of that. Okay, so the work done, according to this definition, is going to be negative QED. Well, now we also know that the work done can be expressed as a change in kinetic energy. Okay, where delta K is K final minus K initial. So K final is going to be 1/2 mv final squared. And what's kinetic energy at the initial point going to be? Well, it's released from rest, right? So its initial velocity is going to be 0. And now we have a relationship between velocity and electric field and charge and displacement, which are all the knowns that were given in the problem. So we're going to equate this definition of work and this definition of work together to solve for VF. We have negative QED equals 1/2 mvf squared. And you may be looking at this and maybe you're a couple steps ahead and you're like, hey, wait a minute. When I square root to solve for final velocity, I'm going to be square rooting a negative number. Are you? Because remember, Q is inherently negative. So when I plug in my negative 1.6 for Q, those negatives are going to cancel. Okay, so let's solve it algebraically first, and then at the very last step, we will plug in our values and see the negatives disappear. So that's going to be 2QE d over m equals VF square root that, right? I kind of did all the steps all at once. Now I can plug in all of my values and I can see my negatives disappear. Okay. Plug all that into the calculator. And we get 4.59 times 10 to the 6 meters per second. Okay? Not too bad, right? So keeping track of the negative signs is probably one of the more difficult aspects, but if we just remember our definitions, let's review real quick. This Q, allow it to be negative or positive, okay? So don't put any negative signs in front if you see that the charge is negative. Wait till you plug in the numbers. So this can be positive or negative. These two, always positive because they're magnitudes by definition. And then this guy can also obviously be positive or negative, okay? So you can review these slides to get some extra explanations. And you can see that we obtained the same answer. So let's now talk about, we were just talking about a point charge in an electric field. Well, let's now talk about 2-point charges, okay? I mean, it's pretty much saying the same thing, right? As you know, we can express the force between two particles as one particle in an electric field or the force between two particles. So we're going to switch now to the case of looking at two particles and the potential energy between them. And the reason why we're going to do that is because in chemistry and biology, it's very common to have ionic solutions made up of a molecule that breaks into its component atoms, and each of those component atoms is an ion, right? For example, salt. So salt breaks into a chloride ion, negatively charged ion, and a positively charged sodium ion. And those can be modeled as point charges, okay? They behave much like point charges, so it makes sense to treat them as such and do some calculations. And so that's kind of our motivation. And so we can define the electric potential energy between 2-point charges using this expression right here, okay? And the way this expression is derived, you don't need to worry about that. There's a little bit of calculus involved. I think in your pre-lecture it mentioned that, so you don't need to know that calculus. Here's the final answer. You get to just use this equation, okay? And the potential energy that exists between two charges, Q1 and Q2, is K, Q1, Q2 over R. So it looks very similar to all of the other equations you've learned, right? You learned that the force is Q1, Q2 over R squared. You learned that the electric field is KQ over R squared, okay? It all looks the same because you can derive, these are all related to each other, right? They're all connected to each other. So let's take a look at this equation here and just note some math facts, right? Q1 and Q2 can be positive or negative. And so depending on their signs, that can change the potential energy to be positive or negative, right? The denominator, R. So the potential energy between two particles, it's going to be large when R is small, right? That's that inverse proportionality. Potential energy can be small when R is big. In other words, as R approaches infinity, as those two particles get farther and farther away from each other, the potential energy will approach zero. Okay, and those are just some characteristics of an equation like this. And we're discussing it in the context of particles in, energy of particles in vicinity of one another. So let's look at some graphs, okay, of our two situations where either the charges are like or are different signs. And as you can see, if Q1 and Q2 are opposite signs, the potential is going to be negative, right? It exists completely under the x-axis or the r-axis. So the potential will always be negative between particles of opposite sign. And here you can see those kind of asymptotes, right? As r approaches infinity, the potential is going to approach zero, right? It's going to creep up slowly and slowly, eventually reaching, in a million years, reaching that axis, right? When r is close to infinity. And then down here, we're looking at when r is getting smaller and smaller, what happens to the potential between them? Well, it gets larger and larger, but more negative, right? It has a large magnitude, but a negative sign. So this is a graphical representation of what we were talking about up here. And so now what about two charges of the same sign? So this is for either negative, negative, or positive, positive. Well, the potential exists completely in the positive area, right, above the x-axis or the r-axis. And we have the same kind of asymptotes going on here, asymptotic behavior. So as r approaches infinity, u does also approach zero, except it approaches it from the positive side. But it does get smaller and smaller magnitude-wise. And then finally, as r gets really small, u is going to blow up and become gigantic, but positive. Okay? So that's basically what this slide says too. So let's talk about a way, we've been speaking about potential and work done. We've been speaking about it very mathematically, right? Letting the negative signs cancel and show us that it's positive, or not canceling and showing that it's negative. And we've been speaking at it from a very math point of view. So I want to bring it up now in terms of a conceptual point of view, okay? And the way that we interpret potential energy of a pair of point charges, we have to think about it a little differently. Instead of thinking about the work done by the electric field, which is technically what we've been defining all the way up here, right? Anytime we talk about work up until this point, we have talked about the work being done by the electric field. Let me just show you in that definition what I mean, right? This is W electric, right? Work done by the electric field, okay? Conceptually, it's hard to imagine work being done by a field. It's much easier for us to imagine work being done by you and me, right? Hands, okay? And so in this interpretation, we're gonna consider the amount of work that you and I would have to do to bring the charges to their current positions from infinitely far away. So in order to make this make sense with the equations up here, you need to understand that this amount of work that you and I would have to do, that's called external work, okay? That's work that you or I or a person would have to do. And the relationship between external work and work done by a field is opposite. It's a negative sign, okay? So anytime we talk about the work that is externally done on something, that's going to have the opposite sign as the work that the field would do, okay? The second thing is look at the second part of the sentence. the work we would have to do to bring the charges to their current positions from infinitely far away. So their initial position is at infinity. Final position is the current position of the problem. Okay, so what we're doing here is we're doing U initial minus U final, right? Which is negative delta U. So we have these two negative signs that are canceling, and that therefore it's going to give us the same sign as if we were speaking about the electric field, the work that the electric field is doing. Okay, so what I want to tell you is that this interpretation, this useful way to interpret U electric, there's two negative signs in that interpretation in order to bring you to the definition that we have been speaking about up until this point, 17.3, okay? So that's just what I want to make you aware of. But so we can use this concept, okay? But it's not going to be exactly the equation. It's not going to translate exactly to the equations we've been using. But let's talk about it. So let's say that we have two charges of opposite signs, okay? They are already attracted to each other. So we would do negative work to bring those charges together from infinity to their current position, right? We wouldn't have to do anything. We would do negative work because they're already attracted to each other, right? Does that make sense? We didn't exert a force to do this work. The electric field did it for us, okay? So that's one way to think about it. Now, what about two positively charged particles? Same sign particles, same sign charges. You would have to do work to bring them from infinity to be close to each other because we need to overcome the repulsive electric force that pushes them apart. And so that's going to give us a positive potential energy, okay? So we can take this idea between two particles and extend it to three or more point charges. And in order to do that, we examine the potential between two charges, and then we bring in a third one, and then we examine the potential energy between that pair and that pair, in addition to the pair that was already there. And it's nice and easy because you can simply add these energies together, right? So we would add the energy of 1, 2 to the energy of 1, 3 to the energy of 2, 3. And we would get the total potential of the system. So it's not too bad at all. And that's what this equation illustrates. So we're adding the potential energy between unique pairs. Okay, we're not doing 1, 3 and 3, 1, right? We're only doing unique pairs. So we're adding 1, 3, we're adding 2, 3, and we're adding 1, 2. All right? So you just need to make sure that you're using the correct distances, the distance between 1 and 2, the distance between 1 and 3, and the distance between 2 and 3, right? So that's kind of the difficulty. In this example, which illustrates this in kind of a word problem, it's done in the pre-lecture, so you can watch the pre-lecture video again to get help doing this example. So I'm not going to do it in this lecture just because it's already existing there. And then there's a bunch of slides here to kind of help you work through it, but I suggest you do it. What I want to do is I want to do this example with you where we, it's a little bit more straightforward, right? There isn't a word problem associated with it. It just kind of lays out the particles, and we're going to focus on the math and getting the math right. So we have 3 particles with different charges, and they're located at different positions on an XY axis. what is the total electric potential energy of these three? So I think the best way is to draw a picture. And because we're going to need is the positions, right? And how much distance is between them. So Q1 is positive, and it's located at the origin, 0, 0. And we're going to denote positive by blue. Q2 is negative, and it's at over 0, up 4, so it's up here. And then Q3 is positive, and it's located at over 3, up 0. Okay, so Q1, Q2, and that's Q2. And so the distance is here. The distance here was 4, I believe, 4 centimeters. The distance here was 3. And since this is a right triangle, I can use the fact that this is a 3, 4, 5 triangle, and that distance would be 0.05 meters, 5 centimeters. So I have all my distances laid out because I know I'm going to need that. I'm going to use the equation K. So we're adding up the potential energy of all the unique pairs. Okay, 1, 2, 1, 3, and 2, 3. And it's really, as far as this goes, it's plug and chug. Remember to keep your signs intact, okay? So the first term, okay, term 1, term 2, and term 3, I'm just going to label them that way because I need to write them out over here. So U12 is going to be 9 times 10 to the 9. Q1 times Q2. Yeah, I'm going to need a lot more room than that. Let's move you over. So 4.3 times 10 to the 6 minus 6. Negative 9.8 times 10 to the minus 6. I'm going to drop my units just so I have room. And then the distance between 1 and 2 is 0.04. And I'm just going to go ahead and write down all this and then calculate it. All right, U1 and 3. 1 is 4.3. 3 is positive 5. And then the distance between 1 and 3 is 0.03. Finally, my third term. Two is negative. Three is positive. And then the distance between 2 and 3 is the hypotenuse of the 3, 4, 5 triangle, which is 5. And so now when I plug all those in my calculator, I will write their answers right under here. I get, luckily I have this. Let's see, 4.3 and 9.8. 9.48, and that is a negative value for the first term. And what are the units? Well, this is energy. The units are joules. And I can kind of see that because you see these coulombs squared go away. This meter, one of the meters go away, and I'm left with a Newton meter, which is also known as a joule. So negative 9.48 joules for the first term. The second term is 4.3 times 5. Second term is going to be 6.45 joules positive. because I'm doing 1 times 3, which is a positive times a positive. And then finally, my last term will be negative, and that's going to be negative 8.82 joules. So when I add those together, I'm definitely going to get a negative number. And the number I get is negative 11.85 joules. All right, so this isn't terrible, right? It's not terrible. A little bit of geometry, nothing crazy. Being careful with your signs. All right, adding energy is supposed to be easier than force vectors, right? Or electric field vectors. That's why we use energy analysis, because the math is a bit easier. The concept is maybe a little bit more difficult, but the math is easier. So here's a schematic and, some information about that example, which you can read through. So let's look at these conceptual questions here. Suppose that you reversed the signs of the 3-point charges in that previous example. If the positions remain unchanged, what would the total electric potential energy be? Well, we can kind of figure that out. Let's do this. Let's copy and paste this part right here. Let's see if it'll let me do that. Oops. And put it down here. Let's think of the signs that make up. So originally, I'll write it in black. This was positive times a negative. This was positive times a positive. And this was negative times a positive. And so now, when we're switching the signs, guess what? Nothing changes, right? We're still going to get a negative number for the first term. We're still going to get a positive number for the second term, and we're still going to get a negative number for the third term. So, we are going to get the exact same result if we changed the signs. Okay? So, to wrap up this section, right, we looked at electrical potential energy. We looked at it from a couple of different viewpoints. We looked at it from examining the work done by a particle in an electric field. We saw that that's equal to negative delta U, okay? And then we can also physically just calculate the potential by using K, Q1, Q2 over R, right? Where if we were doing U final minus U initial, we would calculate the potential of the final position, calculate the potential of the initial position, and subtract them. Okay, so there's 2 different ways to find potential. You can use work done, or you can just manually do the subtraction, right? Do the delta U. And whichever one you do, it depends on the problem and what's given to you. So we saw, right, the electric potential energy of a pair of point charges equals the amount of work you would have to do to move those charges from infinity to their present positions, right? So this is a conceptual explanation, right, where we're saying that the work that we would do is equal to opposite of the work done by the force or by the electric field. And we're examining the situation of moving those charges from infinity, so their initial position would be at infinity, to their present position, which is their final position, right? So it's just a way to conceptually think about this. But in order to use the equations to describe it, we need to recall that the external work done is equal to the negative of the work that the electric force would have to do. And then finally, we can just straight up add the electric potential of more than 2 charges together, okay, by considering a unique pair and adding up the potential between each unique pair.